Okay, so I want to solve the collapse of the wave function using the relativistic slide rule. So first of all, I'm going to imagine a particle here and you create two entangled particles and they go whizzing off in opposite directions to a scientist over here and a scientist over here. Let's call that scientist Alice and call this one Bob. Now let's say that this is Alice's particle detector and this is Bob's particle detector, and let's say that everything inside that circle is a quantum realm, and everything outside that little circle, those little circles, is the classical realm, and on the surface is the interface where measurement takes place. So let's say that Alice and Bob can both make a measurement wherever they feel like, anywhere at all. Okay, and when they make the measurement they might be successful or unsuccessful. They don't know which way the particle is spinning, but let's say Alice measures in this direction to see if it's spinning in this direction. And the answer is no, let's say. Now that causes the particle to collapse into that direction in her particle detector. So now she knows the particle is there. And let's say Bob, just randomly, I'm just going to pick here. So Bob measures here, and let's say he gets a yes. So he finds that the particle is spinning in that direction. These are spin half particles because that distance is half the magnitude. Okay, and they just do that over and over and over again. They just make endless measurements, and then after thousands of times they collate all those measurements, and the average result is a 50% probability of being right. And why is that? That's because, for example, if Alice's particle collapsed that way, if Bob was to measure that way, which is the same direction, he would get a 0% probability of success. If he was to measure in this direction here, he would get 100% probability of success. And that's because, strangely, momentum is conserved so that I'm saying that information goes backwards in times to this point 0 and then forwards so that it happens at the same time, that there is a quantum reality. This becomes Bob's quantum reality, which is the result of conservation of momentum when Alice's measurement creates a classical reality. And the same goes for Bob's measurement. That classical reality goes backwards in time, then forwards in time, so that instantaneously there's a quantum reality in Alice's detector. I'll call that Alice's quantum reality, and the probability of success of her measurement is based on the probability of that quantum reality collapsing round and collapsing there. And the same goes for Bob. Is the probability of success is the probability of his measurement going around to there. Well, actually, she made the measurement over here, so it was the probability of that going to there, but it didn't. It went the other way. So and that probability is calculated by from this angle, and just briefly I'll just say that that angle is, the probability is the cosine of half of that angle squared. That's the probability, and the reason is that by geometry this angle here is half, and if you, that's a right angle there, and if you so the cosine is that, and then the square of the cosine is that, and it looks like it's about 30% probability of success. I mean, actually she measured this way, so yeah, no, so there was actually a 60% probability of success, but it actually failed, so okay, so we got to this situation, and now I want to explain how the collapse happens. We already calculated from the angle theta that the probability of collapse was 30% in this case, and if we were to do lots and lots of experiments, on average we would find that the probability of collapse is exactly 50%, as I've written up here. Okay, so now let's come to my theory based on the relativistic slide rule as to how it happens. So first I want to note, and I'm going to put this in yellow, that these angles, these lines are always parallel. There's only one line of simultaneity. You could say there's quantum reality is one dimension in space. It only has one dimension in space, and as for time, which I'm going to call frequency, it's not even in quantum reality. So there are no dimensions of time or space-time, because these are, I'm going to say that these are Riemann spheres, and time and space-time don't actually enter those spheres at all. In order for there to be a time direction, this has to rotate around to there, which means that this will rotate around to there. So here we've still got our angle, but this is rotated, and this will rotate around so that they meet, so that at this one point here, which in special relativity we call an event, a moment of now, let's say, and there's only one. So this rotated around to there, which means that rotated around to there as well, and you'll find that they always end up on the same side. And now as a result, we find that we've constructed the relativistic slide rule, because now we find we've got two lines of simultaneity. We've got Bob's line of simultaneity, and we've got Alice's line of simultaneity, and we just got this one event happening here. And now those two purple lines, which are They've been on the surface of the Riemann sphere, which were not parallel. Now they've both gone around, and now they're both parallel and in the middle there in the same direction. And that's there. However, they have no extension. Neither space nor time has any extension. They're right on that spot there. That's a moment of now. But if we construct the relativistic slide rule before this collapse, we find that this is going to be L, and this length here will become L squared. Same down here, L squared, and as I pointed out up here, the probability is 30%. That's only 30% of the total distance, which is 1. So the probability of that collapse happening is only 30%. Now let me put in the other ones. This is actually time here. Now that's space-time. There, notice that time and space-time are not inside the Riemann sphere, so they're not part of quantum reality. I'll put it here as well, space-time and time. This is before the collapse, but it's like the relativistic slide rule is the solution to the problem of there being a direction in time or a simultaneous event. And of course Penrose describes the reason as being this tension due to gravity. So L over T squared would be the self-gravity that he's talking about, and that's got to collapse. So as it goes round, all of this collapses. So in a way, this is the frequencies out here. This is ahead. This is ahead in time, but it's going to collapse and become now. So you could say that that's the future, and that 30% refers to the probability of that future becoming a moment now, a now moment. So there's a 30% probability that that future will happen due to this collapse. Okay, this is the final one to do with collapse of the wave function, and this might just be a total flight of fantasy, but it's my prerogative. So anyway, I said that the wave function collapses to this point here, and these are spin half particles, and they collapse to this one event here, and the probability of that happening is here, L squared, that length there, because that's L. It's L, therefore that's L squared, so that's the probability. And I said that that's a space-time event Okay, so now I'm just going to go nuts and say that it's a moment of consciousness, and that it rises from the collapse of these, what I'm going to call mental events. So in a way I'm saying that that's like the quantum reality. Now I'm going to call that the mind, and call the surface the mind. And so this might be qualia, and I'm going to say that this might be the physical universe. There's another one there. Or the body. So in Buddhism you've got the 5 skandhas, you've got the body, you've got feelings, 3 perceptions, 4 thoughts, and 5 consciousness. So they're the 5 skandhas according to Buddhism. And now everything inside here is in the past, and the further you go into that point here, that's the very beginning. So let's just call that, it's the singularity, or let's just call it the soul, just to be completely hilarious. And that's the beginning of time. So that's T for time. That's the beginning of everything, basically. Beginning. And remember, this is actually true, that in order to calculate the distance for a space travel, you go 2 times that, which is that plus that. So it's like you go from one physical surface, one body, to another body. So you could almost say you go from one celestial body, celestial body, can't spell it, to another. So that would support that idea that that's a physical universe, and that's another physical universe. That's like a mental universe. It's the one we each have as individuals. And this is the beginning of time. And collapse is due to the rotation of these to become a single event. Yes, that's a single event there, consciousness. And so that's where we perceive the physical world.